Alright, in this next part what we're going to do is we're going to find the average shear stress in a 3-inch pin that connects member CG to the bottom floor beam assembly. Here's this member CG, and we're talking about the connection that's down here at the bottom. In the previous part we saw a little bit of that detail where we have these two I-bars that come down. They're connected by this 3-inch diameter pin to this floor beam assembly that's down here. This is the pin that we're going to be taking a look at in this part of the problem. And this is just another drawing of that. Is the way it be oriented in sort of real life is that member is vertical. Here's the pin and here's the floor beam. It would be coming in and out of view in the board. So take a moment to familiarize yourself, orient yourself in the drawings to what's going on. While you pause the video to do that, I'm going to bring out another little assembly piece here. And so what I've got is this pin that is connected to these little pieces here that represent then the floor beam assembly. What you don't see is the I-bars themselves in that particular image. All right, so we're going to go calculate the average direct shear stress, and the flow of the loads through this system are as follows. Here's the I-bar that's responding with this total of 200 kips, 100 in each one, and here's these two plates that are part of the floor beam assembly that are pulling the other direction. And it's this 3-inch diameter pin that then connects all those together. And in effect, what's going to happen here, if we start cutting free body diagrams, we've got one part that's bearing on the bolt shaft and the other part bearing on the other part of the bolt shaft. This one would represent that 100 kip force effect. This one would represent that 100 kip force effect. So let's start getting a few little drawings in here to try to better understand what might be going on. Right? So let's cut through this little part of the bolt shaft and draw a free body diagram. Freeing everything out here, we'd have our I-bar there, and we then have our plate and channel there, and then we got the nut of the nut head of the bolt, and then a portion of the bolt shaft coming through here. Now, equilibrium wise, we have an axial force of 100 kips in the I-bar, 100 kips in the plate that's attached, and that means that there is no shear force on that bolt cross section right there. So that's kind of an important piece to understand. Now, if we walk our way back further, cut ourselves through then that bolt in between those two pieces, that's called the shear plane, by the way. Then let's look at the free body diagram of the I-bar. Here's again that nut associated with the bolt, and I'm going to show just a tiny little portion of the bolt shaft coming through, right? And so because we're between the two plates, we don't have that 100 kip to the left at all. All we've got are the 100 kip force coming from the I-bar. Okay, let me shift over there a little bit. And then for equilibrium, then we've got to have shear in the bolt. And by simple equilibrium, then it has to be equal to 100 kips. Right, now, from a sort of perspective drawing of that bolt, then here's that cross section of the bolt, and then we've got the other end and the nut or bolt head that's sitting out here, etc., going around, and then we've got this part here pulling, tugging on it. There's from your I-bar, and here is this shear in the bolt. Right? It's parallel to that surface. So the average shear on that bolt, that shearing stress, is going to be the shear force divided by that bolt area. And in this case, then we've got 100 kips. This is a 3-inch diameter if we're not in the threaded portion, if we're in the, and in this case we wouldn't be here with this 3-inch diameter bolt. Then we have the gross area, so that's just pi times r squared. Note the units, kips over square inches, so force over length squared. That if we don't have that unit correct, then that tells us that we did the math wrong. And so we'll have 100 divided by pi divided by 1.5 squared, and that will be a stress of 14.1 KSI, right? Kips per square inch. So a little bit bigger than we had for the axial stress, which was 13.3 KSI in tension. Now here we don't put anything else here. It's understood tau average. That means tau is a shear stress. We won't worry about the sign or direction for now about the shear. But that gives us our answer for our average, oops, not 14.4, but 14.1 KSI.